Alrighty, in this video we're going to be looking at the graphical relationship between the function, its first derivative and its second derivative. In particular, x-intercepts, turning points, or all stationary points really, and just what is the actual relationship there. And hopefully this video will help you make sense of the algebra you do when you determine things like stationary points. Why do we let the first derivative equal 0 to find them? And for points of inflection, why do we let the second derivative equal to 0 to find them? So graphically, here we go. I've got a function here. It's f of x is equal to 2/3 x cubed plus 6x squared plus 16x plus 13. And this is what it looks like. If I zoom out, it goes on forever in both directions into negative infinity and positive infinity. But the cool part and the most important part is this bit here. So first thing to identify, and remember, this is just graphically for now, I can see that I've got a maximum, a local maximum here at -4 and 2 1/3. And I've got a local minimum here at -2 and -1/3. And somewhere between them, I must have a point of inflection, because somewhere here, it goes from concave down to concave up. So somewhere in here, I've got a point of inflection, but I'm going to leave that for now. I've prepared these two vertical lines here. And you can see that these two, x equals -4 and x equals -2, correspond to these turning points. And they're going to be useful in the next section here. Also, what I've got prepared is f dash x. So in Desmos, if you express a function in terms of f of x, if you do f dash x, it'll automatically sketch you the derivative. So I'm going to plug that in here. And what do we see? Well, the most important aspect and the first thing to grasp is that these turning points, or at least the x-coordinate of these turning points, corresponds to x-intercepts at -4, 0 and -2, 0 of the first derivative. Okay, so these turning points, no matter your function, and I'll show you another one after this, correspond exactly to the x-intercepts of its first derivative. And now hopefully it makes sense why we use the first derivative to find those turning points when we do it algebraically. We find the first derivative and we let it equal 0. Because if you take any function of x and you let it equal 0, you're solving for the x-intercepts. Okay, so if we take this first derivative function, which is a parabolic shape, and we let it equal 0, we effectively do null factor law in this case, and we would find that the x-intercepts are -4 and -2. But more importantly, we recognize graphically they correspond to these stationary points of the original function. Now, that's one thing. The second thing I want to talk about is once you've got the first derivative, let's look at its turning point. It has a turning point here at -3, -2. But the -3x value is the main thing I want to look at. I'm going to sketch another straight line, x equals -3, and I'm going to do it very similar to the other ones here. Make it less opaque and make it dotted. Maybe it's 0.3 is best. Okay, so that's another important equation, x equals -3, because it is the turning point of my derivative function. And what that corresponds to is my point of inflection of my original function. So my original function had a local max and a local min, and we said somewhere in here we're going to get a point of inflection, and this is it here at -3, 1. And that corresponds to the stationary point of the first derivative. So we can go even further here and say, okay, I'm going to pause a sec and go back in time. We said to find x-intercepts of the first derivative was to find turning points of the primitive function. So if we found x-intercepts of the first derivative, we found turning points of the primitive. If we can find an x-intercept of this thing's derivative, x-intercept here, I'm going to actually go ahead and show that, f double dash x is a straight line, and you'll notice that its x-intercept is at here at -3, then we find its primitive, which is the second derivative's turning point, and hence we find the point of inflection of the very original function. So by doing the first derivative and then the second derivative, we find an x-intercept, which tells us the first derivative's turning point, and the first derivative's turning point finds us the point of inflection, which is why algebraically, without having to sketch anything, to find the any point of inflection, we find the second derivative, we let it equal to 0, because this red line is the second derivative. When we let it equal 0, we get the x-intercept, which tells us the original function's point of inflection. Okay, if that didn't make sense, totally understandable. There's a lot there. Go back and watch the video again and again and again until you actually fully grasp and you go, oh, okay. Original turning points can be found by first derivative letting it equal 0, these x-intercepts. And points of inflection can be found by finding by letting the second derivative equal 0 to find its x-intercept. Let's look at another function here. I'm going to turn all these off, and we're going to look at another function that I've got prepared here, which is this g of x function. And turn it on, and it's a bit more up here. I'll zoom out a bit. It's a bit more funky looking, but I can see graphically that I have a stationary point here, and potentially, maybe not, a stationary point somewhere up here, maybe at -2. It looks like it might be a horizontal point of inflection, but let's see. So to determine those stationary points, I need to take the first derivative and I need to let it equal 0. So g dash x is this blue function here. I'm going to put in a dotted line, or maybe change it to red to make it stand out. And its x-intercepts are here at 0. So as anticipated in the original function, this is a turning point, that x-intercept, and this doesn't cut the x-axis, but it does bounce off it, so it still counts as an x-intercept here at -2. So if I type in x equals -2, actually I already have x equals -2, I'll put that back in, and we go all the way up to the original function, we find that as suspected, yes, this is a stationary point. Now it's not a local maximum or a local minimum, but we can investigate further and find out what it is. Spoiler alert, it's a point of inflection, a horizontal point of inflection. But notice that by doing the first derivative, let it equal 0, we find the x-intercepts which correspond to stationary points in the original function. The next step is to do the second derivative and find where that equals 0. So g double dash x, and we find we have x-intercepts here at -2 again, and we also have one here at -2/3. So I'm going to put in x equals -2/3. I'll make that dotted, 0.3 opacity. All right, so we have another, that didn't work. Oh, it's purple, that's why. Okay, so we're going to follow, we already knew that the -2 x-intercept was here. Okay, but this -2/3 is going to correspond to this point here of -2/3 and 9.519. Now, the y coordinate is not as interesting right now because all I want to show you is that if I turn off the second derivative now that I've used it, this second intercept of the second derivative here corresponds to the turning, the point of inflection here between this concave down nature of the curve and the concave up nature of the curve at this local minimum, or absolute minimum in this function's case. So absolute minimum here, and somewhere it clearly has to change from concave up to concave down. And the point where it changes is this point of inflection, and of course to find it graphically or algebraically, we have to look at the second derivative, this green function, and look where it intercepts with the x-axis. Now, quickly, the red function intercepts at -2, and so does the second derivative, which indicates, if that's the case, that on the original function, that x-coordinate, so here at -2, it is both a stationary point and a point of inflection, and we call them horizontal points of inflection. So we get concave down into concave up, but it's not a turning point. It doesn't continue concave down like this, and this part doesn't continue concave up like that. It is a bit of like an S sort of shape, and so it's a point of inflection, but it's also a stationary point, because at this exact point, if I zoom right in, the tangent to this line is exactly 0. Okay, it's just y equals negative, y equals 19. That would be the equation of that tangent. So hopefully my ramblings were clear enough. Hopefully you now have a better understanding of the relationship between the original function, the first derivative of a function, and the second derivative of a function, and realizing that it's mostly just a relationship between the x-intercepts of the first and second derivative and the corresponding points in the original function. It may take you a couple of watches of this video to like fully grasp it, but I promise you having a deep understanding of this is just going to really benefit your algebraic work when you start solving for stationary points and determining their nature and other branches of mathematics like that. So hopefully this video helped. See you in the next one.